Okay, good morning. So we'll be continuing with the application of Newton's law of cooling. So Newton's law of cooling states that the rate of change on the temperature of a body, or I'm just going to change this one to just T, is directly proportional to the difference in the temperature of the body and its environment, T sub m. So the Newton's law of cooling follows the law of conservation of energy. Okay, so that energy is neither created nor destroyed. It's just transformed from one form into another. So similar in the Newton's law of cooling, so the temperature increases or decreases. So it increases because it gains heat, and then it decreases because it dissipates heat. Okay, so in Newton's law of cooling, it states that mathematically that the rate of change in the temperature of the body, which is T, with respect to time, is directly proportional to the difference on the temperature of the body and that of its environment, T sub m. Okay, so in measuring the temperature of a body, it always depends on the environment where it is subjected. Okay, so the temperature of a body cannot go beyond. Okay, so the temperature of the body cannot go beyond the temperature of its environment. So it depends on whether it will increase. So if the environment will be warmer, and then its temperature will decrease. Okay, so if the environment is colder. So for example, if we have a pan and then we're going to place it inside an oven, so the oven would have its temperature. So let's say it has a temperature of 350 degrees Fahrenheit. So the temperature of the pan cannot go beyond 350 degrees Fahrenheit. So that would be the maximum temperature that can be gained by the given body. So similarly, let's say we're going to place a soda inside a refrigerator. So if the refrigerator, let's say, would have a temperature of let's say 0 degree Celsius. Okay, so therefore that soda could not have a temperature below 0 degree Celsius. Okay, so it could be closer to 0 degrees Celsius, but not below that temperature of the environment. Okay, so in representing the principle of the Newton's law of cooling, so we have this rate, and so similar with what we have before, so we could transform this one into a differential equation. So by introducing a proportionality K to that of the difference of T minus T sub m. And then again, so this is a separable equation. So dt over T minus T sub m is equals to K dt. So in here, so what's variable here is the temperature of the body. Okay, so the T is the variable here. T sub m is constant. Okay, so we are assuming that the temperature of the body or the temperature of the environment is constant. It does not change. So while for, of course, the time changes, and then the K is the proportionality constant. So we can now solve the differential equation, so using the separable equation. And since T sub m is constant, so therefore this is the same as ln of T minus T sub m. And that would be equal to Kt plus C. So exponentiating both sides, so that will lead to T minus T sub m is equals to Ce Kt. So giving us the general formula for the Newton's law of cooling. So for the Newton's law of cooling, so since this is a law, there's no other formula, okay, so aside from this as compared to that of the growth and decay. So in growth and decay, so it depends on the statement or on the relation that was provided on the problem. But in Newton's law of cooling, so since this is a law, so we're following the same formula. So there's no derivation that is needed here. So we could always use this formula. So remember that we have different values here. So that T is the temperature of the body at any time. So T sub M is the temperature of the environment. So we have to distinguish. So since we are talking about two temperatures here, the temperature of the body and the temperature of the environment, so we have to distinguish which is which. Okay, so the temperature of the body is the one that we are talking about, so the one that is moving, okay, or that's the object. So while that of the temperature of the environment is where that object is subjected into. So in a pan that is placed inside an oven, the temperature of the pan so corresponds to the temperature of the body. So the temperature of the oven so corresponds to the temperature of the environment. A soda placed inside the refrigerator, the soda would correspond to the temperature of the body, while that of the refrigerator would serve as the temperature of its environment. So C then is the arbitrary constant. K, of course, is the proportionality constant. Proportionality. And of course, T is our time. Okay, so those are all the variables as well as the constants for the formula in using the principles of Newton's law of cooling. Okay, so to better understand on how to use the process, so let's proceed. So with our example number 1. So for our example number 1, so we have the temperature of a metal is 20 degrees Celsius. It is submerged in a large body of liquid of temperature 5 degrees Celsius. So after a minute, the temperature of the metal dropped down to 10 degrees Celsius. So when will the metal's temperature be 6 degrees Celsius? And after 30 seconds, so what will be the temperature of the metal? So let's provide our given. Okay, so we don't need to let T, okay, and T sub M, or pwede rin that let T, okay, so to be equal to the temperature of the metal, so which is the body, and then the T sub M, it is submerged in a large body of liquid. Okay, so that is the temperature of body of liquid. So since that is where we submerge the metal. So from here, so we can now say that the temperature of a metal is 20 degrees Celsius. So that means initially, the temperature of the body is 20 degrees Celsius. And it is submerged in a large body of liquid of temperature 5 degrees Celsius. So since the temperature of the body of liquid is our T sub M, so T sub M is equals to 5 degrees Celsius. So after a minute, the temperature of the metal dropped down to 10 degrees Celsius. So after 1 minute, so from 20 degrees Celsius, it drops down to 10 degrees Celsius. So it decreases because we subjected the metal into a cooler place, okay, or into a cooler body of liquid of 5 degrees Celsius. So therefore, it will drop. So from 20 to 10 until the minimum, so will be 5 degrees Celsius. So our first question is, so when will the metal's temperature be 6 degrees Celsius? So when will be the metal's temperature so be 6 degrees Celsius? So that would be, so what would be the time? So when this one is close to 5 degrees Celsius, okay, so that would be 6. The next one is after 30 seconds, so what will be the temperature of the metal? So we have to take note of the consistencies or the consistency in the use of units. So we are using minute, okay, so on the given, so therefore if that is 30 seconds, so that would be 0.5 of a minute. So what would be that temperature? Okay, so this is a very direct problem So we'll be using the formula T minus T sub m, so it's equal to CEKT. So since T sub m is already given, so which is 5 degrees Celsius, so this is T minus 5 is equals to CEKT. So similar with the growth and decay, so we can get the value of C, so from the initial value, and the value of K, so from the other initial value. So it says here that when T is 0, okay, so when T is 0, the time is 0, so the temperature of the body is 20 degrees Celsius. However, this doesn't follow that since time is 0, RC is already our T. It's not the same case as with that of the growth and decay. So it's because there is, or the formula that we are using here involves the temperature of the environment, so which we need to subtract. So that is why when T is equals to 0, T is equals to 20 degrees Celsius, so that would be 20, so minus 5, so will be equal to CEK times 0. So from here, so C is 15. So it's not the same as 20. So since we need to subtract the temperature of the environment. So from there, so we can say that T minus 5 is equals to 15 EKT. And so to get the value of K, so that is when T is equal to 1 minute, so the temperature is 10 degrees Celsius. So that is why 10, so minus 10 minus 5 equals to 15 EK, so that is will be 1. So 10 minus 5 is 5 over 15, or 5 over 15 is equals to E raised to K. So take the natural logarithm of both sides. So that would make K to be equivalent to ln of 1/3. So our K is ln of 1/3. So giving us our final working equation to be T minus 5 is equals to 15 E raised to T ln of 1/3. So this will become our working equation. So T minus 5 is equals to 15 E raised to T ln of 1/3. And then, so let's solve. So for A, that is when the temperature is 6 degrees Celsius, so what will be that time? So to solve that, so we have our formula. So T minus 5 is equals to 15 E raised to T ln of 1/3. So this is 6 minus 5 is equals to 15 E raised to T ln of 1/3. So this would be 6 minus 5 is 1, all over 15 is equals to ET ln of 1/3. So taking the ln of both sides, so T then so would be equal to ln of 1 over 15 divided with ln of 1/3. And so you can try doing it on your calculator. So just pause it. Okay. So pause the video first so that it won't show the answer right away. However, I do have the answer already. So this is approximately, or that would be equal to 2.46 minutes. So that will be the time. So to reach 6 degrees Celsius. So for the second one, so that is, so what would be the temperature? So after 30 seconds. So after 30 seconds, so since the time of 0 is 20 degrees Celsius, after a minute it's 10 degrees Celsius. So if it is after 30 seconds, so that should be in between 10 to 20. Okay, so when T is 0.5 of a minute, so what would be the temperature? So using the same formula, so we can see that so T is equals to 15 e raised to 0.5, so ln of 1/3. So the -5 so will become +5. So 15 e raised to 0.5 ln of 1/3 plus 5. So pause the video first. So try to do it on your calculator so you can get used to it. But again, I do have the answer already. So my answer is 13.66 degrees Celsius. So again, so this is in between 10 to 20 degrees Celsius. So in between 10 to 20 degrees Celsius. Okay, so that's on how to use the Newton's law of cooling. So it's exactly the same as that of the growth and decay. The only difference is with introduction of the temperature of the environment. Pero on how to do it, the process is the same. So next, so the second example is something that it changes its environment. Okay, so there is a change in the environment. But I'll be discussing later on whenever we are dealing with this type of problems. So let me read first. So at a certain time, a thermometer reading 70 degrees Fahrenheit is taken outdoors, so where the temperature is 15 degrees Fahrenheit. So 5 minutes later, the thermometer reading is 45 degrees Fahrenheit. So after another 5 minutes, the thermometer is taken back indoors where the temperature is fixed at 70 degrees Fahrenheit. So what is the thermometer reading? So 10 minutes after it was brought back indoors. And when will the reading to the nearest degree return back to its original reading of 70 degrees Fahrenheit? So for our given here, so we have actually, so we could use, so since there are two environments here, so we could use T1, a thermometer. So that would be the temperature of thermometer. And then this one is taken outdoors. So that would be T sub M1. So that is the temperature of outdoor. And at a certain time, so that thermometer, so T1, so T1 of 0, so we have 70 degrees Fahrenheit. And then it's taken outdoors, so where the temperature is 15 degrees Fahrenheit. So TM1 is equals to 15 degrees Fahrenheit. So 5 minutes later, the thermometer reading, so again, so T1, so after 5 minutes, so it will drop down. So because the environment is colder than the temperature of the thermometer. So which is 5 minutes later, the thermometer reading is 45 degrees Fahrenheit. So 45 degrees Fahrenheit. And then, so after another 5 minutes, the thermometer is taken back indoors. So where the temperature is fixed at 70 degrees Fahrenheit. So it goes back indoor. So after another 5 minutes. So that is another 5 minutes. So 5 and 5. So that would be 10. So T1 of 10, so is equal to, I do not know. Okay, so it was taken back inside. Okay, so it was taken back inside. However, I do not know. Okay, so what is that temperature. Okay. However, from outdoor, okay, so the thermometer is taken back inside, and the temperature inside is different with that of the outdoor. It says here that thermometer is taken back indoors where the temperature is fixed at 70 degrees Fahrenheit. So therefore, from here to here, so we have from this would be outdoor. Okay. However, so for the indoor, so we could have our T sub 2. Okay, so T sub 2 is the temperature of the thermometer. So temperature of the thermometer. Then Tm2, the temperature of indoor. Then initially, so T2, I do not know. Okay, so what's the initial? So the initial is after 10 minutes. Okay, so or another 5 minutes that it was taken indoor. So since we need to get that one, so T sub 2 of 0 is actually the same as the T sub 1 of 10. And which is still unknown. And then, so we have our Tm2, so which is the temperature indoor, and that is 70 degrees Fahrenheit. So this is the time that it was brought back indoor. So the first question is, so what's the thermometer reading 10 minutes after it was brought back indoors? Okay, so for our required, so that is T2 of 10. So 10 minutes after it was brought back indoors, so what would be that temperature? And the second one is, when will the reading to the nearest degree return back to its original reading of 70 degrees Fahrenheit? So nearest degree, okay, so to 70 degrees Fahrenheit. So I'm assuming, so when will be that time? So let's say the nearest degree to 70, so I'm assuming that would be 69.99 degrees Fahrenheit. So the nearest degree, pinakamalapit to 70 degrees Fahrenheit. Kasi if that would be 70, approximately, that would be too ideal. So let's say 69.99. So this is what is due with this problem. Okay, so there is a change on the environment. So from the original one, so where it was exposed to outdoor, and then it was taken back inside. Okay, so indoor. So to solve this one, so we'll be using the same formula, but we'll start with outdoor. So that would be T1, so minus Tm1 is equals to, so pertaining to indoor as 1, CEK T1. Okay, so take note here that the arbitrary constant usually changes. The arbitrary constant usually changes depending on the environment. Okay, so depending on the environment. However, the proportionality constant is not. Okay, so the proportionality constant K is it's something that is unique. Okay, so it's something that is unique with that of the body. Okay, so as long as it is subjected to whatever would be the environment, but K will always become constant. Okay, so it doesn't change. Unlike with that of the arbitrary constant. That's the difference between the two. So when we say arbitrary constant, it is constant, but it could be any other constant. So that's why it was termed as arbitrary. Okay, so it is a constant, but it could be 1, it could be 2, it could be 0.5, it could be -2. So that makes it arbitrary. However, the proportionality constant K is different. The proportionality constant K is inherent. It's a property of a certain material which doesn't change. So regardless whatever would be the environment where it will be subjected to. Okay, so that is why, so regardless whether we're going to subject our thermometer outside at a temperature of 15 degrees Fahrenheit, and we're going to transfer it going back inside at a temperature of 70 degrees Fahrenheit, so the proportionality constant K of the thermometer so will just be the same. So in short, fixed or constant yung K. Yung C lang yung nagbabago. Okay, so take note of that. K is constant. So, we have, so when T1 is 0, so we have the temperature of the body to be equivalent to 70 degrees Fahrenheit. 70, and Tm1 is 15. So it goes to C E K times 0. So this is 1, so therefore C is 55. Correct? So 55. So C is 55. So therefore we have now our new formula to be T1 minus 15. So it goes to 55 EK T1. And then for the second given, so when T1 is 5, so the temperature is 45. So therefore, so T1 minus 15 is equals to 50. No, sorry. So T1 is 45, so minus 15 so was to 55 EK, then we have 5 there. So 45, so minus 15, so we'll have 30 over 55 is equals to E raised to 5K. So taking the natural logarithm of both sides, so K is equals to ln of, so we could have it by 5. So that would be 6 over 11, so divide it with 5. So making our general equation to be T1, so minus 15 is equals to 55 e raised to T ln of 6 over 11 divided with 5. So that is our general working equation. So to get our first requirement, it says that so we need to find first, so what would be the time, okay, so what is the time, so 10 minutes or after another 5 minutes. So when T1 is 10, okay, so what is T1? So T1 minus 15 is equals to 55 e raised to T ln of 6 over 11 divided with 5. Okay, so T1 so would be 55, so e raised to 10 ln of 6 over 11 divided with 5, and then plus 15. So do your calculation. So 55 e, so 10 plus 15. So the answer is 31.36 degrees Fahrenheit. So since T1 is 36, so we can now conclude that the time initially, okay, so for the second environment, so this would be the temperature of the thermometer, so 10 minutes, okay, so after 10 minutes that it was, or right after it was taken inside that of the indoor. So that will be 31.36 degrees or degree Fahrenheit. So which is equal to T1 of 10. So T1 of 10 is equal to T2 of 0. So that makes 31.36 degree Fahrenheit. So from here, we can now create, okay, so the new formula. So instead, so we could have T2, so minus Tm2, so will be equal to CE K T2. So Tm2, so when T2 is 0, so we get that T2 is 31.36. So 31.36, so Tm2, so based from the given is 70 degrees Fahrenheit. So 70 is equals to CEK times 0. So giving us to have C to be equivalent to, so 31.36 minus 70, so that is negative 38.64. So since that would be our C, and then K is constant, so K is ln 6 over 11 divided with 5. So therefore, our formula then so would be T2, so minus 70 equals to negative 38.64. So e raised to t ln of 6 over 11 divided with 5. So this is our now new working equation. Okay, so for our second formula. So in here, so we need to find, so what would be T2 of 10. So after 10 minutes that it was brought back, okay, so after 10 minutes that it was brought back, so when T2 is 10, so what is T2? So we'll have T2 minus 70, so equals to negative 38.64 e raised to t ln of 6 over 11 divided with 5. So T2 then would be equal to negative 38.64 e raised to, so t is 10, ln of 6 over 11 divided with 5, and then plus 70. So T2 is, so 58.50. 58.50 degrees Fahrenheit. Then for our second requirement is, so when T2 is approximately equal to 69.99, so what would be the time so it would take for that? So let me copy the problem or the formula. And we could have, so T2 is 69.99, so minus 70 is equals to negative 38.64. So e raised to t ln of 6 over 11 divided with 5. So this would be negative 0.01, so divided with negative 38.36 equals to e raised to t ln of 6 over 11 divided with 5. So take the natural logarithm of both sides, so t then, so will be equal to 5, so ln of 0.01, so divide it with 38.36 and divide it with ln of 6 over 11. So t then, okay, so I need a calculator for this, so hopefully I could compute this one. So we have 5, so ln of 0.01, so divide it with 38.36 and divide it with ln of 6 over 11. So 5 ln of 0.01 over 38.36 ln of 6 over 11. So t then is 68.07, and that will be in minutes. So actually, to make it equal to 0, okay, so that would take an infinite amount of time. Okay, so that's why we have a very close to 70, so which is 69.99. So that would be 68.07 minutes. And if we're going to add more 9s there, so let's say 69.999 or 69.9999, okay, this one increases and then it approaches to positive infinity. Okay, so that will be Newton's law of cooling. Okay, so for additional examples, so you can refer to the next video. Okay, so the video for which is on our module. So that will be all for Newton's law of cooling. Thank you.